So okay, till previous video we have calculated the noise input referred or noise for 5 transistor OTA, and we analyzed the individual transistors contribution to the output noise, then we referred it to the input. The in previous video we referred the noise to the input, like first we calculated the output referred, not referred, but the output noise current, the output short circuit noise current. This was calculated. Later we referred it to the input using GM of this transistor or GM of entire design. So if output is short circuit current noise, then you can refer it to input using GM of the block. And if we have calculated anyway output, not short circuit, if we have calculated output noise, then we can refer it to using means voltage gain. Simple. So if we have output noise voltage, then we can refer it to input noise voltage using voltage gain, that is A square. So these are the two ways to refer the net output noise that we have calculated due to the contribution of all the transistor to the input, because overall we compare with the input referred noise only. In the same way, one more means non-ideality, that is your offset. So first we will calculate the total contribution of device offset to the output current, then we will refer it to the input as an input referred offset, or we can calculate the output voltage due to the offset or mismatches in the devices, then we can refer it to the input. So first I would tell little about the offset. Actually, in general op-amp, if both the inputs are ground or they are shorted anyway, then what should be the output? Ideally it should be 0, this case or this case. So if even at the same voltage at the input, if output is not equal to 0 for V plus equal to V minus, means both the terminals are equal, output is not equal to 0, means there is, or not at input, but I can say there is an offset in design. But how can we measure it? By referring it to the input. What does it mean by referring to the input? Referring to the input means simply, if my inputs are still at 0, and by adjusting this voltage, this I call V offset, by providing this voltage, if I am able to make my output 0, then I can say this offset is nothing but. So in general there should not be any output for shorted inputs, but if there is some mismatching between the devices in this, inside this transistor, inside this amplifier, then there is a possibility that output cannot be 0 for the shorted input. Then in that case what we will do, we will short the input yet and we will apply some extra voltage that can make my output is 0, and that particular extra voltage is known as the input referred offset, or that is the amount of voltage that is required to make my output to 0. Okay, so now we slowly move to the transistor level, because the transistor level is important in interview perspective. So let me see. So ideally what is expected, if my input are shorted, my output should be 0. If it is not like that, then there is an offset and we have to model it at the inputs. So what is the reason can be there? So these two input pairs, so reason can be that the input pairs cannot have the same nature. In the same nature, I mean to say they cannot be exactly identical, and if they are not identical, and even we designed them identical, there may be the many possibilities that they will not remain identical after fabrication. So what are the possibilities? In M1, what are the things? Design perspective, there is W by L, that you always consider. Second thing is that VTH. Third thing is mu n COX. So there are many possibilities between M1 and M2. Maybe we have designed the identical M1 and M2, but after fabrication, width cannot be same, length cannot be same. There may be some other effects, and VTH1 cannot be identical for the both the devices, and many other possibilities. Not many other, but yeah, there is a possibility that oxide capacitance of 1 is not equal to oxide capacitance of 2, because this capacitance is nothing but depends on what? Epsilon ox by Tox. May be possible in designing the oxide may not equal, oxide thickness may not equal, and also depending on the material, some material discontinuities, epsilon may also vary, but these effects are very unimportant. These are not that much important when we consider the mismatching. But majorly the important thing that we consider as a mismatch is BT mismatch. There are also ID mismatch. If we look for any transistor specs in any particular technology, then these two parameters are mentioned there. In BT mismatch, there is a coefficient, the sigma VT, that we will say that is nothing but ABT divided by root W to L, or root area. So ABT is a mismatch coefficient that is defined in every means or can say PDK. It is defined in PDK. I'm not going into the depth of this, but yes, ABT is a matching coefficient. If we want to reduce this, to minimize the mismatch, we have to reduce the sigma, means deviation of this VT mismatch. Least the mismatch between two devices, better is the matching. So one more thing from here, we can see that sigma VT is inversely proportional to root area. So if we are increasing the area, then we can control the or we can reduce the mismatching. So this is also stated by the Pelgram's law. This is not important for the interview, but I can mention Pelgram's law, that if we can increase the area of individual device, means equal. If we are increasing the area of both the devices, then there is a possibility that mismatching will be reduced. The reason is that simple. If we are having two devices of the small size, then any particular mismatching in the edge can cause a huge mismatch. I mean to say that if I have M1 of this particular area and M2 of this particular area, then during the design there will be the possibility that any roughness in the edges may not result into the equal area. Then there is a possibility of mismatch. So now point is that this roughness is more visible if overall area is small. Now if overall area is large for the device after everything, then this roughness will not matter much. If this is one can say overall 1 picometer over this width of 1 nanometer, then you can say here the percentage will be less. If this is again 1 picometer over this length of, can say, 10 nanometer, then we can see that this edge roughness of 1 picometer is very small. Any defect is visible when we observe at a small scale, but it will not be visible in a large scale. You can also understand this thing by this. If there is a small water and there is a color drop we want to drop, it is a 1 ml color drop, and this is my 10 ml water, then it is easily visible. Somewhere the droplets will be visible, colored will be visible. And if there is a big container containing 10 liter of the water, then what is the significance of 1 ml color? It will be of no significance. It will not be that much effective. Simple logic is there. Any roughness after the design, it will be more visible in the lesser area devices. It will be less visible in the larger area devices. So simply by increasing the area, we can reduce the VT mismatch. This is the one way. Now exactly how VT mismatch we will compute the effect of it at the output, that we will see. And other mismatch is also defined as the current mismatch as sigma ID, that is also written as AV or instead of AVT I can write it AI by root WIL. So here this thing is defined in percent micrometer. AI is in percent micrometer, and so from here again more area ID mismatch can be reduced, or any mismatch can be reduced, will also be reduced. Okay. So now let me go to the exact modeling of this mismatch model of transistors. If there is any question asked like that, what do you understand why VT mismatch and how it will be visible, then you can say this thing. Otherwise, it is not that important. The main thing is that how to model it. So from our knowledge, if we make this input to 0 and there is any mismatch between these two devices, then I will say that VT mismatch I can result here if this is 0 and DC at this is also 0, but there is a mismatch between these two devices, and this mismatch can also be written as del VT, output short circuit current I want to see. Okay, so this is the way of modeling the input mismatch, the input pair. First I am considering M1 and M2, then I will see the contribution at M3 M4 later. So if DC shorted, these outputs are inputs are DC shorted, but there is a mismatch, means if suppose this is the DC voltage VCM, so for this there is a particular VT value and there is a particular ID. For here there is a VCM for that particular VT and particular ID in DC conditions. In both the branches, that the ID is equal ID and ID. That is a 2ID. Okay, 2ID or 2I naught. But if VT is slightly here and there, I will write this as a del VT. And simple from the equation of current, we can see that what amount of current should flow here is not exactly same the what amount of current should flow through the M2. Because from the current expression we can see current is what? Some K by 2 WIL VGS minus VTH square. Okay. So from here we can see that this VT is different for both the devices. So simply ID1 is not equal to I2T, which ideally should be equal. If my VT is something, sign is not that important, del VT, then I can say that there is overall net current is generated, which is, if I say here this is a VT only and I put the DC ground, then I can say there is a 0 ampere flowing and there is also DC 0 ampere flowing, but on top of that there is a one more current, that is GM del VT, and this is 0, so no current from this side. Overall this ISC is nothing but equal to GM del VT. And similarly the mismatch can be seen, I will consider this VT plus del VT on the M2 side, it can be also considered at the M1 side. Overall I can say that the GM is what? This GM is nothing but GM1 or 2. Okay, because we consider the GM of both the devices are same, this is equal to GM. So overall mismatch output short circuit current will be what? GM del VT. So this is the effect of mismatching between the input pair. So directly what you can see, if the question is asked that how will you see the this mismatch between the devices, and the input, then you can simply say that you have shorted the DC, and top of that there is a BT mismatch. Due to that, one branch will consist the del BT current, and other branch will be zero current, because zero current is due to the DC current, which is or I can say in general it is the last signal current, which is zero, because both the side I have shorted the input to the ground. Now this additional current that is flowing to the device toward the device 2 is due to only this del VT term. It will, direction can be anything, I am not worrying about that, but yes, the point is that the net amount of the current will flow across the output. That is the output offset current. That is the output offset current due to VT mismatch at input pair. Now same thing can be considered, or wait, one thing that I am missing here, this PMOS should be this. Okay, in the same way we can consider the BT mismatch between the current mirror. So interview, what is the best way? Just say that, or instead of saying anything, just model this voltage, that del VT, at the input of the devices. Okay, as we have mentioned, now again I am shorting these inputs, but I am considering this mismatch, the VT mismatch between these two devices output, and I want to short the output, and short circuit current I want to see. Okay, so from here we can see, if there is a mismatch between these two devices, then we are free to consider del VT here. And again, if the input are shorted and there is a the current mirrors are not getting voltage from anywhere because the input devices are off, but due to this del VT, there is a possibility that there is a generation of means some VGS on any side. It may be on M3 side, it may be on M4 side, but overall we will see that what amount of current that will go to the output is nothing but GM of 3,4 into del VT. Okay, so del VT is a voltage that can be modeled as a voltage source at the input of the both the transistor M3 and M4. So we can model mismatch as a voltage source. Okay, so if I am considering M1 M2, then we have considered here this input VT mismatch we have considered, and in here at the input of M3 and M4 we have considered. So ISC is what? ISC is GM34 del VT. Okay, so overall current will be what? I will remove this thing, this is not required here. So what is the overall mismatch current that is flowing? Overall mismatch current ISC total will be what? This is my, yeah, this will be my, okay, again this is the offset current, the direction that not matter that much, but yes, we can consider it as, okay, GM12 del VT plus GM3,4. We will see the sigma VT, which is nothing but ABT by 2WL, or better to say that for del VT I can say directly, just refer this to the input. What is this? This is nothing but ISC offset at output that we are getting divided by GM. Okay, so what is this? This is what GM12 del VT 12 plus GM put del VT 34 divided by, in to overall GM is GM of 12. It will result into del VT of 12 plus, but this mismatch is appearing with some constant. So overall I can say that V offset, input referred offset is what? It is nothing but del VT of GM12 transistor plus this GM34Y GM12 del VT34. Okay, so one thing that we know that if I want to calculate the standard deviation function, which was previously I was doing something incorrect. If this is my function, okay, and it is a function of some variable, yeah, this function is my function of two variable x and y, and if I want to calculate the standard deviation of this function, then what will be that del fy del x square del x square plus del fy del y square standard deviation of second function. So this is the total of standard deviation. Because we represent the noise in terms of the standard deviation, then you can write like this. Otherwise, this is enough. This expression is enough for the interview purpose. If we want to more, then how we can reduce this expression in terms of standard deviation? Because we know the standard deviation of del bt, or can say sigma, that is a standard deviation, that is nothing but abty root area, which is wl, or I can say any for any vt, it can be abt square by this is the total expression. Okay, so what we have, what we offset at input is what directly del vt 12 plus gm34y gm12 del vt34. Okay, so sigma of input total will be what? If I will respect in a differentiate this del bt12 with respect to del bt12, then what will be here? 1 and what will be standard deviation? 1. Its differentiation is 1, and it's a it is what? Del bt plus this is what? gm34, 1 square means 1, gm34 divided by gm12 square 2 del bt 34 square. So overall we can see it can be written as a bt square y wl for 1 2 plus gm3 y gm12 square abt34 by. So overall sigma of input referred offset is nothing but it is a root of this. Okay, this is the overall input referred offset. How to reduce it? Just what we can do, one thing is that increase the area is one choice, area increment is one choice. Second choice is that we can increase gm12 or we can reduce. Okay, so these are few ways we can do. And more thing that is required in this offset analysis is nothing, I think. Yeah, this is enough. So how we proceed, we will see that if the input are shorted, there is a current, or there is a means if the inputs are shorted, if the inputs are shorted, there is output. And to identify that why this output is, we went to the structure of this OTA. In this 5-pack OTA, we have seen that who is responsible for this offset, and we found that input pair and current mirror is responsible. And these are the following mismatches possibilities are there. This is the physical explanation of that. And you will see that by shorting the input, we can just model this mismatch as a voltage source, and we can put it at the input of the two pair or input of the pair. So this is something that I was doing incorrect, I think, maybe. So that's why I cut it. And after the short circuit current we got at the output, we just refer to the input just by using the GM that we have seen here, so that we can compare two structures. Okay, so this is enough for this video. In coming video we will see some other topics. So thank you.